We're going to look at salts as they can react as both acids and bases. So once you decide whether the salt can act as an acid or a base, it's going to be a simple weak acid problem or a simple weak base problem. A neutral salt. A neutral salt is one that consists of cations of strong bases. So sodium hydroxide, calcium hydroxide, potassium hydroxide. This is the cation whose parent base is a strong hydroxide. And the anion is from a strong acid, HCl, HBr, HNO3. So if both ions in the salt are cations and anions that have strong parent acids and strong parent bases, then they have weak conjugates that are weaker than water and can have no effect on the H plus or OH negative when dissolved in water. So the pH will be controlled by the water itself and will have a pH of 7. These are your neutral salts. A neutral salt is also created when you do a strong acid, strong base titration. Again, you can see you form your salt from the sodium hydroxide and hydrochloric acid. So when you put the salt and it's dissolved in water and the only species floating around are the water and the sodium and chloride ions, the only one that has effect on the pH is the water, because these cations and anions can no longer react with water. The pH will be 7 when you titrate a strong acid with a strong base. So when your titration curve, your pH right here will be 7. An acidic salt is where the anion has neutral properties, but the cation is the conjugate acid of a weak base. So your anion from hydrochloric acid or nitric acid, but your cations are coming from a weak base. So they're going to form a strong conjugate. So the ammonium ion comes from the weak base NH3, so since the base is weak, the conjugate acid that's formed is stronger than water and can continue on to react with water by donating a proton to form the hydronium ion and give you an acidic pH. Again, an acidic salt is typically going to be an ammonium salt. Could be a tetraamine salt or a diamine salt, but they're going to be formed from these amines, the basic structure of which is ammonia. So they're going to form strong conjugate acids of the weak base. So the ammonium ion will act as an acid with the water to form the hydronium ion, and you're going to need a Ka value since you are forming the hydronium ion, an acidic salt. When you titrate a strong acid with a weak base, you're going to get this type of salt. So strong acid HCl with the weak base ammonia forms ammonium chloride and water. The ammonium chloride salt would dissociate to these ions. This ion, being the weak conjugate of a strong acid, will not further react with water. This ion will continue to react with water since it's the strong conjugate acid of a weak base. Strong meaning stronger than water, not a strong acid like HCl, but a strong conjugate. So it will continue to react with water. It will be the acid donating its proton and forming the hydronium ion in an acidic solution. You'll not have a basic solution because ammonia is present. It's the presence of the hydronium ion or the hydroxide ion, remember, that gives you the pH. So this will give you a pH less than 7. So if you have a titration curve, that pH value at the equivalence point is not going to be 7. When you follow over to that pH, it's going to be less than 7. So here's a typical problem for this type of salt. You write the equation for the dissociation of the salt and you look at the ions that are present, and you determine that this ion comes from a strong parent acid, so will have no effect on the pH. This ion comes from a weak parent base, so will react like an acid. Write the chemistry out. It's crucial that you do this. Recognize that you're forming the hydronium ion. Once you have the chemistry, then you can put your ice in. Without the equation, there's no point because you don't know what is being formed or what is controlling the pH. So put your ice in, same way you always would. This is nothing more than a weak acid problem. Once you have your x squared over 0.1, that's equal to your Ka. Again, you have to have a Ka value. This would be the hydronium ion would indicate an acid pH. When you find X, it is your H+. Look back at your reaction, the hydronium ion. That's what X is. So you simply take the negative log of that to get the pH, and it should be slightly less than 7. So you've got an acidic salt forming an acidic pH. A basic salt will be a cation that has neutral properties coming from a strong base like sodium hydroxide, potassium hydroxide, and the anion is now the conjugate base of a weak acid, so it's going to continue to react with water. So the acetate ion from acetic acid, the cyanide ion from the weak hydrocyanic, the fluoride ion from the weak acid hydrofluoric acid. Take that ion, place it in water, and now you have a reaction where this ion is going to be a basic ion. So it's going to take the proton from water, reforming the original acid and leaving you with the pH controlling hydroxide ion. The reason this forms a hydroxide is because this conjugate base, okay, will act like a base in reforming the acid and now leaving you with the hydroxide ion. The F negative in this example is the strong conjugate base of the weak acid hydrofluoric acid. Therefore, it will act like a base. It's a stronger base than water. Remember, you're going to need a Kb value because you're forming the hydroxide ion. If you titrate a weak acid with a strong base, you're going to get this type of salt. So hydrofluoric acid, weak acid, strong base is going to create a salt whose cation, okay, is not going to change the pH, but whose anion will continue to react with water to form the hydroxide ion. The pH at the equivalence point, when you titrate this, will then be greater than 7. So when you draw your titration curve, you're going to have a pH at the equivalence point that is going to be greater than 7. A typical problem, you've got the sodium fluoride solution. You write the complete dissociation of the ions. You pick the ion that's going to continue to react with water. The sodium ion could not. It's the conjugate of a strong base. But the fluoride ion is a strong conjugate of a weak acid. So you've got to think about what the chemistry would be. Obviously, the water acts as the acid. That's going to reform hydrofluoric acid and leave you with the hydroxide ion. Once you know the chemistry, it's simply a weak base problem. You set up your ice, and you've got x squared over 0.3 equals Kb. You need a Kb because X is the hydroxide ion. This is a Kb reaction. A Kb reaction always forms the hydroxide ion. Unfortunately, if we go back to the beginning of that problem, so I'll go back a little bit, Notice they gave you a Ka in this problem. They did not give you the Kb for the F negative ion. They gave you the Ka for hydrofluoric acid. Why? Because that's the most typically published value. You have to be able to connect them correctly. So once you have your ice and you put your x squared over 0.3, the biggest step is to remember that x is going to be hydroxide and this is a Kb. And then you have to find the Kb. The Kb will be equivalent to the Kw over Ka. The reaction to solve for Kw is always Ka times Kb. Remember, pH plus pOH. Okay? Now you have a Ka times a Kb giving you a Kw. So you solve for the Kb. You solve for x, you take the negative log of that, but then, don't forget, you have to subtract that value from 14 to give you the pH. This would have been the pOH, since x was the OH negative. A little bit of thinking that you have to do when you have a weak base problem. You have to make sure that you know X is OH negative. You have to make sure that you know you need a Kb. They might give you a Kb, but chances are they're going to give you a Ka, and you have to use this to find the Kb. Then, once you negative log that value, you have to get back to the pH by subtracting the pOH from 14. So, a couple of extra steps. When you titrate a weak acid with a weak base, you're going to get a salt that has two strong conjugates, and they can both react with water. The pH would be controlled by which one of these has the stronger K value. If the Ka is greater than the Kb, it will be acidic. If the Kb is greater than the Ka, then it will be basic. So we'll talk about these types of problems more in class. You can qualitatively predict, okay, but you won't know the exact pH. So if the Ka is greater than Kb, it's going to be acidic. If Kb is greater than Ka, it's going to be basic. And if they're equivalent, it's going to be neutral. But you would not be able to come up with the exact pH without doing math. Again, a quick review of the salt reactions. A basic salt, okay, has an anion that can continue to react with water like a base, forming the hydroxide ion. The acidic salt is going to form a cation that can continue to react with water to form the hydronium ion.